Hello friends, so today we will learn about red-black tree and see how to insert the nodes in the red-black tree. So red-black tree is also called RB tree, which is a type of self-balancing binary search tree with a special attribute called color. So here you can see that in the binary search tree we have this in the red-black tree we have all the nodes are either red color or a black color. So the nodes are giving color red or a black. Actually, this coloring of the node ensures that the longest path from the root to leaf is no longer than twice the length of the shortest path. What does it mean? It means if we have any tree with the 5 nodes, let's say this is a tree, something like this. So here the path from the root to the leaf, here you can see this is actually 1 and here you can see this is actually 3. So this is more than double the shortest path. So this is not a balanced tree. To make it balanced, the structure must be either like this, so the 5 nodes will be distributed like this, or it will be distributed like this. So here you can see that the path is no more than twice the shortest path. So this coloring is something which ensures this thing. Like in the AVL tree, we have a balancing factor that ensures that tree should not be spanning towards one direction. Normally, we want the balanced trees to reduce the memory size and also to reduce the running time. So red-black tree is also a height balanced tree. So we'll see more about it. Basically, we have 4 properties of RB tree. Property number 1 says that root is always be black. The second is nil is considered to be black, which means that every non-nil node has 2 children. So this is also called sentinel. So whenever you make any RB tree, whatever the node you are inserting, we are assuming that there is one nil is attached to each node, which is black in color. So property 3 says black children rule. That means children of each red nodes are black. So we know that in the tree we have either red nodes or a black node. So if any node is red, then the children of this node must be black. Then black height rule is an important property of this RB tree. It says that there is one parameter, we call it black height BH, such that the downward path from V to a nil has exactly black height, black real nodes. What does it mean? It means if you have a RB tree, something like this, then black height says that if you are going from the root to the leaf through any of the path, then the number of black nodes must be same. So let us say if I follow this path to go to the leaf, this is one path, this may be other path to the leaf, this may be third path to the leaf, this may be the other path to the leaf. So if I follow any of the path from the root to the leaf, the number of nodes in the path must be same. This is called black height rule. Now insertion. Insertion means we want to insert a node in the RB tree. So the first property says whenever you insert a node, the node color must be red. So every time when we are inserting any node in this tree, its color must be given red. And then when we have to make sure that every time the root must always be black, because we have seen in the property of the red-black tree, and there is also one interesting property that if there is any red node you can find in the RB tree, its children must be black as well as its parent must also be black. So whenever we insert any node in the RB tree, there may be a possibility that its properties are violated. Now we need to fix up. So to fix up these properties, we need to make rotations. We will see how to make these rotations to fix up our RB tree. Now we need to understand what are the cases when we have a violation of the RB tree properties. So it says that whenever a new node is inserted, so whenever you are going to insert a first node, as we know, if this is the first node you are inserting, we don't have any RB tree and this is the first node. So by property of insertion, we are going to make it red. But we know that the RB tree must always have a black root. So this is a kind of violation. So this is very simple to fix it. You just change this red color to black, and this is now means resolved. Now we have this root node which is black in color. Second thing is, if parent of a new node is red, so we will always be having a violation whenever the parent is red in color. So for example, so we will be using some terminology we need to understand. This is our tree, these are the nodes, this is a kind of let's say in this case it is a root node, and we are going to insert one node, and this is the node, something like this is we have inserted. So whenever we insert a node, we need to look into these three nodes into the consideration. Now this is something called parent, and this is called grandparent, and this is a sibling of this grandparent, which we are calling it uncle. So whenever you find this parent color to be red, if this parent color is red, then only there is a violation. If the parent color is not red, then there is no violation. Now if there is a violation, then we may have three kind of means problem. You can say we have three cases here. Now these three cases are defined on the color of this uncle. So if the uncle is red, you are in the case 1, but if the uncle is black, you may be in case 2 or in case 3. We will see what is case 2 and case 3 in the next slide. So let us look to the key points of inserting the nodes in the RB tree. We may have some discrepancies while inserting. So where the sibling is red, so as I told you, means this is a scenario. You are inserting a node. This is your parent, this is your uncle, this is your grandparent, and if this uncle color is red, we are in also we need to understand that this problem is always there when parent color is red, then only there is a problem. If this is a black, then there is no problem. So we are assuming that the parent is red, then we need to see in which problem we are fallen. So we look at the uncle color. If the uncle is red, then we are into problem, and we can simply resolve the problem by changing the colors. Means there is no need to do rotations in the case 1. This is called case 1. We can simply resolve it by changing the colors. But if this uncle is black, in color, then you are in case 2 or case 3, and in these two cases you need to do some rotations to resolve the violations. So we'll see one by one how to resolve case 1 and then case 2. Let us see all the cases one by one. So case 1 says new node uncle is red. So this is a scenario. We have this arbitrary where this color is black, this is red, and we are going to insert this node. Now you may consider scenario. Let's say this is something, let's say 15, this is 6, this is 20, and I am going to insert a node, let's say 10. Then using the binary search tree, it should be the right child of this node. So here this is red color, and new node will always be red color, so there is a problem. And then we need to look to the uncle is also red in color, so we are in case 1. So what to do? The strategy is change the color. Simply change the color, we can resolve this problem. Now what is required? Change the color of the grandparent of a new node. So we need to change the color of the parent, the uncle. Now this is parent, I am writing PT, uncle is UN, and the grandparent is GP. So we need to change the color of parent, uncle, and the grandparent. And grandparent will be marked as a new node. So we need to make this color as a black, this as a black, and this as a red, and this resolve it. And also one more step is required. This is something, the new node which you are inserting, let us call it X. So also means we need to change this X to the grandparent. So now this will be our new X, and we need to proceed from here. But here you need to notice one thing, because this is the only size of the tree. So when you make the changes to resolve the case 1, you maybe change this black color to red. So this again violates a property of RB tree. The RB tree root must always be black. So if this is a root node, then we simply change it to black color. But if this is not a root node, then you need to look to the previous structure, and then you need to proceed as per the rule. So we look into the case 2. So case 2 needs a rotation. So the strategy to resolve this is we need to do a rotation. So before we do the rotation, we need to understand what is said to be case 2. So case 2 is something when you have a new node which is a right child of a left parent. This is a right child, which is the X node. This is a right child of a left parent, or if you have, this is named X, if you are left child of a right parent, then this is said to be a case 2, and we are assuming that the sibling, means the uncle color, is black. Here the uncle color is black, then you are in case 2. So what is required when you are in the case 2? In the case 2, anti-clockwise rotation at the parent node. So if this is the new node you are inserting, and this is a parent, this is uncle, and this is your grandparent, and if this is if this is red color, this is red color, this is black color, so we need to make an anti-clockwise rotation. If this is a right child, you need to make a left rotation. If this is the case, the left child, you need to make a right rotation and make parent as a new node. So after doing the rotation, this X node will be shifted to this node. Now this will be the new X after making rotation. So these are the two things required to resolve case 2. So what we are doing actually, if we are applying to solve this, we will be doing like this. So this is our A, this is our C, and we are doing a rotation like this. So it will be here N, this is your B, and also you need to shift. So this is earlier X and it goes to B, so now this will be your X, and you put the color. This is black, black, red, red, means there is no change in color of these nodes. The only change is in their position, and also the X will be shifted to the earlier parent. If we are in case 3, again we need to do the rotation as well as we need to do some color changes. So before we resolve this case 3, we need to understand what is case 3. So case 3 is a situation when this new node is a left child of a left parent, or if a new node is a right child of a right parent, then it is said to be a case 3. So to resolve this, we need to follow this step: clockwise rotation at the grandparent node. So if you look at this, this is something X which we are inserting. This is your parent, PT, this is your uncle, and this is your grandparent. So we need to make a clockwise rotation. If this is your left child, we are going to make a rotation like this at the grandparent. If this is a scenario like this, then at the grandparent we are going to make a rotation like this, and then exchange the color of grandparent and the parent. So after making a rotation, we need to swap the colors of a parent and the grandparent. So let us have a look here. What we have to do is, so first we need to make a rotation from here. So if you make a rotation from here, that means this particular node will be becoming the right child of this, so you can see here that A will be coming here, A and C. So this is the first step we have performed here. Second is exchange the color of grandparent and parent. So this is your parent, this is your uncle, this is your grandparent. So we need to change the color of grandparent and parent. So grandparent, this A is actually going to be red and this B is going to be black. So B will be black and A will be red, and C is already black and this is red. So now you can see that your root is black. So this is how we can resolve case 3. So we have seen that if we are going to insert any node in the RB tree, we may got stuck in any problem, and these problems are defined as case 1, case 2 and case 3. So let us take an example and then we can see how to do the rotations if it is required. So first insert 3. So first I am going to insert 3. So whenever you insert any node, because we don't have any node, this will be the first node. So this is the first node I have inserted, and as a rule I will make it red, but because it's a root node, so the property says if it is a root node, make it black. So this is our answer. Then insert 9. So when you insert 9, we will be following the binary search tree. So 3 is the node which is black color, and then you insert 9 and we will make it red. So there is no violation. The parent is black color, so there is no violation. Violation will only come when the parent is red color. Then we insert 23. 23 will be, I'll start from here. 23 is more than this node, more than this key value, so 23 will be here. Then this is also red color. Now you can notice here, as I told you, that all the nodes are having their nil child, which is actually a black in color. So if you look into the scenario, the parent is red, definitely the problem is there, and then you need to look at the uncle. The uncle color is black. So when the uncle color is black, you will be either in case 2 or in case 3. So here this is a right child of a right parent, so we are in case 3. So in case 3, what is required? We need to make a rotation at the grandparent, means we have to make a rotation from here, and we need to change the color of the parent and the grandparent. So first we will make a rotation at here. So what will happen? It will be like this: 9, this is 23, this is 3. And you can see here that this is actually your red color. This becomes a black, this becomes black, and this becomes red, and this becomes red. So again, after making a rotation, now the property is being fixed, and there is no kind of problem, because there may be a possibility that when you come out of any case, you may fall into the other case. So here, when you come out of the case 3, we are safe, means we are not fallen into any other case. And then we have this 3, we have this 23, this is black color, red color, and we need to insert 4. So 4 means we have chrome here, and 4 should be something like this. Now this is red color. Now because the parent is red, we are in case 1, we are in problem, we are in case 1. How we find that we are in case 1? Looking into the uncle, because uncle is red, we are in case 1, and it says we need to change the color to solve the problem. So we will change the color of the parent, uncle and the grandparent. This will be black, and this will be red. And also we need to change this new node position to this X here. Now we have no tree, means above this particular, means this is the root node, and the root node must always be black, so you make it black. So your tree is something like this. This is the root node, black in color, this is black in color, and red in color, and we are safe now, means there is no violation in the RB tree, so we can proceed further. So now we have to insert 7. To insert 7, what we need to do? Okay, just make it a tree here. So we have this tree 9, which is black in color, 23, black in color, 3, black in color, 4, red in color. Now you are inserting 7. The 7 must be inserted like this, which is red in color. So now again, look into this. The parent is red, we are in problem. Now which problem? We look into the uncle. So here we have a null node which is black in color. So this uncle is black, we are in a problem, and this new node X is actually a right child of right parent. That means we are in problem number 3. This is case 3. So in case 3, we need to make a rotation from the grandparent. This is grandparent, we need to make a rotation. This is one thing, and the second thing is we need to change a color of this node, means the grandparent and the parent. So how we can do this? So we can do this like this: 9, 23, which is not affected, but when you make a rotation here, it will be something like this: 4, 3, this is 7. This is black color, this is black color, this is red color, and this 4 is actually red color, which need to be changed after the rotation, so it becomes black, and this black becomes red. And now this is again means arbitrary properties. All properties are satisfied. You can also check the kind of the black height property. So if you go from this path, 2 black nodes are there, it's okay. If you go from this path, this is also 2 black nodes are there. If you go from this path, 2 black nodes are there, so the black height property is satisfied. Whenever you make rotations, whenever you insert any node, you need to check this property, black height property. So now inserting node, this value 60 to this tree. So how do you insert 60? When we insert 60 into this tree, so it will start from the root node. 60 key value is more than this 9, we go to the right side. 23 is less than 60, again we go to right, and 60 will be inserted as a right child of this node, and we'll make it as a red. So we'll check to the parent color is black, so there is no violation. Again remember, there is only a violation when the parent color is red. So this is black, though there is no violation. We can proceed further to insert the next node. This is 5, so we start from this. 5 is less than 9, we go to the left child. 5 is more than 4, we go to the right child. This is 7, so we'll be inserting 5 here, and we make it red color. So you can see here the parent is red, that means there's a problem. To look to the type of the problem, so we look to the uncle color. So this is the parent and this is the uncle. If you look at this, this is the parent, this is the uncle. Uncle color is red, that means we are into the case 1 problem, and it's resolved by simply changing the color. So you can just change the color. This becomes black, this becomes black, this becomes red, and this X will be shifted to this node. Now further you need to check. So this is what is required in the case 1, but again the problem may not be solved because you need to check with the next, means next parent. So this is the node, and you look here to the parent. Now this parent is black, and fortunately this problem is solved, but you may find that this may be red, and then in that case you may fall into some other case, and we need to apply the steps. So hope you have understood how to do the insertions by doing the rotations and changing the colors. Looking into the complexity of insertion procedure, so here you can see that I'm assuming that you are already familiar with the insertion procedure, so we will just have a look to the running time. So in this insertion procedure, you can see this is the same as binary search tree. We need to start from the root node, and we need to keep comparing with the key values with the node values, and if this value is less, we go to the left side. If the key value is more, we go to the right side, and we keep on moving like this. And because this is a balanced tree, so we need to do at most log and comparisons. So in this RB-insert, means if you look at the binary search tree insertion, this is actually log and complexity is there. But in this insertion procedure, you may find there is one procedure that is called FIXUP, because whenever we insert any node, you may be fallen in any case, and then we need to resolve. And to resolve, this is a FIXUP procedure is called. So what is this FIXUP procedure? This is a FIXUP procedure which tells you how to deal with case 1, case 2, and case 3. And you will notice here that this is something while loop is used, and this while loop is the main which may incur some cost. But the beauty of this algorithm is that you cannot have more than 2 rotations anytime. You can insert any key values in the RB tree. You may need to do only 2 rotations at most. You may be doing no rotations, or 1 rotations, or 2 rotations, but not more than 2 rotations. So if you look at this while loop, so this shows that how to deal with the case of means case 1, and in the case 1 we are simply changing the color, and it will be keep on calling until you get rid out of it. So definitely when you are changing the colors, you will be getting out of this case 1 and you may be falling into the case 2 and case 3. And again, as we said that there are only 2 rotations are required, so you will be doing some means changing the node colors and doing rotations at most 2 times, so it will take maximum of log n time. So the total time is a log n here, which you may assume as a constant because there will not be more than 2. Running time of the RB insertion procedure, so log n time is actually required for the insertion, and the log n time you may say is required for the fix-up procedure. So as a whole it is big O of log n time. So the RB tree insertion takes order of log n time. So thank you very much. Hope you have understood the fundamental properties of RB tree, its definition, and how to insert the nodes in the RB tree. And if you want to see more videos on computer algorithm, subscribe to my channel. Thank you very much.